Hello. So, thank you. So today I'm going to talk about hacking and profiling Ruby for performance. My name is Daisuke Aritomo. My friends call me Oshoyu. And I'm a member of the RubyKaigi NOC, which is a network operations center. So it's kind of the Wi-Fi team. I was like dragging cables here and there from day zero. So yeah. And I work at CookPad as my day job. So let me introduce CookPad first. Yeah, did anyone notice the refrigerators over there? Actually, those are from CookPad. Yeah, those refrigerators actually run Ruby. The Ruby code controls the locks. And if anyone wants to build Ruby-powered refrigerators, join us. And one more thing. We're doing a kind of a look-back RubyKaigi event in Tokyo. It's the 18th of May. So it's kind of, the point is that we're kind of doing a hands-on as part of the event. So if you got really excited here at RubyKaigi, please consider joining us here. Please come to our sponsor booth for details. The CookPad booth is just over there outside this hall's doors. So please visit us. OK, so let's start. About this talk, I'm going to talk about how to profile and tune a Ruby web app that you know nothing about within 8 hours as part of a performance tuning competition for fun. So I have a question for you guys first. Do you like the word performance? Yes? OK, everyone loves it. Everyone loves performance. So here's the challenge. There is a performance challenge competition called ISUCON. I don't know whatsoever contest. Contestants are given 3 VMs, computing instances, and a very slow web app. It's slow to the point it's practically unusable. Now, contestants have 8 hours to do everything to this code, and they may request a 60-second benchmark during the contest. So when we request a benchmark, there's a benchmarker server, and the benchmarker server sends our VM a whole ton of HTTP requests to our VM. And the benchmark results are our score. So the goal is to get the best score. Actually, there was another talk concerning this contest, ISUCON. It was done today, and it's actually done, but it was really interesting. So I recommend you guys checking out afterwards. I think all talks are going to be on YouTube, if I'm right. So yeah, please check this out. OK, so I said the contestants get 3 VMs, computing instances. They include a Ruby app, which are implemented using Sinatra and run on Puma. Nginx is included, and MySQL. MySQL is also on the server. So, and also, implementations of the same app in other languages are also included, like in Python, Go, Node.js. The initial performance is kind of tuned to be the same, designed to be the same. So it is said that there's no difference between the languages. So yeah, basically, we're just speaking about make this web app server as fast as possible within 8 hours. You can't scale, you can't buy more servers, you can't expand your servers, but you can do everything else. So yeah, the main loop is kind of like contestants hack around with Ruby code, then run the benchmark, get your score, get baffled, maybe joy, and do it over and over. And the highest team with the highest score will win. So while there are many aspects and possible things to improve our score, today I'm going to talk about these things to what can we do in ISUCON. So why Ruby is a great language to compete in ISUCON, not Python, not Node.js, but why Ruby, and how to track down and profile slow code on the C Ruby level, and what future Rubies need to shine in future ISUCONs, if there are any. Now, I'm actually not going to speak about configuring Nginx, Linux, and those kind of things, although they're really important to get a good score in ISUCON. This is RubyKaigi, so I'm just going to focus on Ruby. And of course, monitoring on the system level and preparation for Itamae recipes. We do a ton of those things, but today we're just going to focus on Ruby. Yeah. So almost everything's permitted. I just said I'm going to focus on Ruby, but there is a ton of SQL things too. Adding effective RDBMS indexes is OK. Killing n+1 SQL queries is OK. Just in case n+1 SQL queries are queries done in loops. So in this case, user IDs is a Ruby array, and you can see that there is a query launched every single time in loop. Replacing suboptimal algorithms is OK. Trying utilizing server resources to the very most is OK. Caching is OK. And of course, upgrading to Ruby Master is OK, because as Sui-san said in the morning talk, the Ruby Master is the fastest Ruby on Earth. Yeah. So we have so many things to do. Where should we start from? This was the loop I just introduced. Hack around this Ruby code, run a benchmark. But the important thing is to know where to do hacking. That's where profiling kicks in. And profiling gives us hints what to do next. But before we dive into profiling, I just want to introduce why Ruby is a great language to do ISUCON. Well, dancing with Ruby. This contest is practically you'll be given 500 to 1,000, not 1,000, but 500 to 800 lines of Sinatra code, which is not really tiny to read and completely understand in 8 hours. But we can, after all, we're writing Ruby, so we can empower Ruby. Let's do a code side comparison. I've extracted some code from the same endpoint. Details aren't important, but I think you can see that Ruby is really more compact, and that helps us reading time, save reading time, and save writing time, of course. We have mighty arrays, hashes, and enumerables. We have really much handy methods that don't tend to exist in other languages, like map each with object, sort by. Almost anything is possible, and those really come in handy when tackling n+1 queries. This is my favorite, monkey patching, time.remove now. I think that any of you don't understand this, but yeah, sometimes you have to remove now from time. So need something in the standard library, just build it on site. And another more hacky thing is running binding IRB or pry in production. Does any of you do this? Oh yeah, I've run those yet, OK. Stop real benchmark request using binding pry or IRB. You can write code in binding IRB. Of course, after all, it's a REPL, so yeah, it's a place to write code. And confirm it works, and copy to your editor and save it. OK, great. Of course, I don't do this at a cookpad. It's just for competition technique. Please be assured. OK, so let's get back to performance. Challenges in Ruby. You start the benchmark button. You get a no method error because you left somewhere new that you didn't know. No method error, no method error. That happens. It's fixable. It's just I'm just joking around. No worries. Let's hope RBS type prof and other projects can solve this problem. So we have. I think that performance challenges in Ruby boils down to 3 points: profiling the accurate bottleneck, and trying to utilizing 100% CPU system resources in Ruby, and achieving high concurrency. Beforehand, I'd like to introduce a saying, don't guess, measure. Random improvements, yeah, I said that you get a really slow, unusable network code. You just look around and there's so many things to improve. Making random improvements is, well, okay, but those won't really take you anywhere. Spending time to fix non-real problems is kind of the last thing you want to do in an 8-hour time frame. So yeah, accurate profiling is the key. Fortunately, we have a lot of profiler choices in Ruby. There are so many profilers to choose from. Profilers, well, this isn't limited Ruby. Profilers can be categorized into, maybe I'm saying too much, but yeah. There are sort of tracing profilers. They track every single function call, every single code running, but they kind of tend to have a big performance impact. Now, Ruby I'm not saying that they're bad. Big performance impact isn't necessarily bad. Sometimes a really precise profile is needed. Now, RubyProf is one choice. It's based on trace point, but in our case, we're seeing like 5 to 10 times slowdown. On the other hand, we have sampling profilers. Sampling profilers collect samples every 10 to 100 milliseconds, and they have small performance impact. Options are like StackProf and RBSpy. StackProf is based on the Ruby's RB profile frames API, and RBSpy is kind of a new one. It runs as a separate process and reads Ruby's memory through Linux's process VM readv system call. As you can see, these don't have really large performance impact. We only have like 6% slowdown. And in ISUCON, the benchmarker sometimes changes its behavior based on our performance. So tracing profilers can be really a choice here. So our team chose to stick with StackProf just because, I don't know, we like the RB profile frames API. So let's profile. This is the visualization of our profiling results. This is called a flame graph. Let's see how to read this. So the horizontal axis is the benchmark window, and you see many bars on here. Each bar represents a function, and if a bar is longer, it means that it's really taking time in the benchmark. It's spending a lot of time in the benchmark. So say, I'm not sure if you can read this, but I've just extracted one from here. It's a network handler for post API condition that's some kind of API. And we can see that its bar is quite long. So it might be space for optimization. Let's see the code. Yeah, we found the n+1 insert query. So this is kind of how we use profilers in the competition. Great. So let's dive in the internals. The frames come, just as I said it previously, StackProf uses the cRuby API, RB profile frames. RB profile frames is a cRuby API that returns the call stack that was running when, on the timing that RB profile frames was called. So I've prepared a kind of diagram. In this example, function A, method A calls method B, and method B calls method C, and it returns So say we called, for stack growth, called RB profile frames when code was executing the second frame, second position. RB profile frames will return the second call stack, in this case, A, B. So stack growth keeps recording that every 10 milliseconds or 100 milliseconds. But this isn't actually always accurate when multithreading kicks in. I found out that, like this, I prepared some sample code. There is a method that does I/O, it's just comments, but there was actually a kind of long code. This I/O method thinks it does I/O for 5 seconds. And there is another burn CPU, the Tarai function, which takes approximately 5 seconds on my computer. So the flame graph, sorry, it's the upside down, it's inverted, but the flame graph horizontal width should be the same between I/O and burn CPU, but it actually isn't. How come? It doesn't even show any I/O. The red part is burn CPU. I think that's pretty much accurate. It's recursing a lot. And the rightmost part is actually thread join, the most bottom line. So we're really seeing no I/O. This is because how multithreading in Ruby works. Only one thread, I think many of you know, but only one thread can use the CPU at the same time in Ruby. This is because of the global VM lock, a GVL. It works. So in this case, while thread one is using the CPU, thread 2 and thread 3 can do I/O. Say if thread 2 wants to use the CPU, as it's doing in the bottom, it has to wait until thread 1 releases the lock. Now, the reason we didn't see, I'm not really sure, but I think the reason that we didn't see I/O in the previous flame graph is because the current implementation of RB profile frames returns information only about the last active thread, which had the GVL. And threads doing I/O they don't have the GVL, so they have low chances to be targeted. So in this case, the bang represents stack frame peaked by RB profile frames. Of course, thread 1 has the GVL, so when RB profile frames was called 6 times, only thread 1 is getting the attention. So this might make flame graphs kind of inaccurate. I've made a proposal here, adding a RB thread profile frames API, which is a per thread version of RB profile frames. It accepts a thread as an argument. So maybe we can, RB profile frames return the information about only the last thread that has the lock. But if we can specify which thread to profile, maybe we can solve the issue. I hope so. At least it does in my environment. OK, so I've talked about profilers. Next, let's think about utilizing 100% CPU in Ruby. As I said, only one thread can be active due to the GVL. Since we don't have many CPU resources in the contest, ISUCON, just as I said, we have only 3 VMs. We can't scale out. We want to use the CPU as much as possible if we need to. This screenshot is from HTOP. The upwards one is from a sample program written in Go. It just runs 8 threads, burning CPU, and it's consuming 100%. But I've implemented the same algorithm in Ruby, spinned up 4 processes, 8 threads each, and it still isn't eating up all CPU. Well, that's the GPL isn't really a bad thing. Actually, it's wonderful. It protects us. It protects us from multithreading bugs. The reason we don't have to think a lot during multithreading programming is because of the GVL, but still, it limits us from utilizing the CPU. So basically, the empty parts are threads waiting for GVL locks. Okay, to reduce GVL locks, the most easy way to be less threads, reducing threads. Reducing threads, of course, it means less workers, so it's less performance. But Puma supports multiple processes. So, like, say, if we reduce threads, we can increase processes in place. In that way, we can keep the number of workers the same, retaining the same performance, in theory. So tuning Puma for 100% CPU. Just as like said, adding server processes is effective, but of course, more processes is more memory. Same as CPU is precious, memory is also precious. So we need to find the perfect balance between the number of processes and threads. Too many processes means too many memory used. And too many threads means too many threads waiting for the GVL lock. How should we find the sweet spot? This is kind of my work in progress, but I've tried to utilize the new event hook. It's called Ruby internal thread event many hooks. So like it start, stop. The hooks are called when a thread acquires the GVL, releases the GVL, and many other timings. I've tried to integrate those results from the hooks in the profiling, and the right flame graph on the right shows waiting for GVL for like 7% of the time. Actually, in the Ruby 3.2 era, many tools are popping out. Shopify GVL tools and Ivo Anjo-san's GVL tracing gem are, those are doing similar things. But maybe these information are usable for tuning number of Puma threads. So the plan is like this. Try adding Puma threads first, and then check GVL wait time. If the wait time is low enough, perfect. Just go on. Maybe try to add more threads. But the wait time is somewhat high. Maybe we should reduce threads and add processes if memory allows us. Cool. So although we probably can't reach 100%, we might go somewhere near. The last part is achieving high concurrency in Ruby. As I said, getting high concurrency in Ruby is not necessarily easy due to the GVL, but there are many attempts. Falcon is an event loop-based rack server based on async I/O for Ruby. It's just like Python's async I/O library or other libraries in other languages. But it really didn't work well as a drop-in replacement for Puma. I think we needed to rewrite a lot of I/O stuff using those async libraries. So I think it's really a really good choice for production apps in jobs, but we didn't have enough time to rewrite a lot of things in 8 hours. And another option we came up with was Truffle Ruby. Truffle Ruby is a completely alternative implementation of Ruby. But we tried this too, but ISUCON VMs didn't have enough memory for Truffle Ruby. It's kind of a really limited environment, so that's a sad thing. And finally, Raptors could be a really good option. each vector has its own GVL. So Koichi-san said GVL of G isn't any more global. It's vector local. But coming to this RubyKaigi, I've been discovering that vectors isn't really easy at a point. So it could be my next challenge. Well, Ruby is a wonderful language. Does everyone use Ruby? Do they? This is the statistics. There's 2 rounds, the qualifications and the finals. In the qualification round, 70% of the teams use Go. And the finals, 86%. The only Ruby team was my team. It's from the last ISUCON. Previous ISUCON has more Ruby teams, but I just pulled this from the last one. What makes this difference? Well, Go has many features for better performance, so maybe that's the key. Go has Go routines. It's kind of a lightweight thread. I'm not going to step into the real details here, but Go routines makes high concurrency quite easy. And more importantly, since Go routines are embedded into the language, concurrency is really deeply embedded into the ecosystem itself. I'd say, well, any practical Go library has concurrency in mind. Context is passed around. Contexts are kind of a tool to pass down the state of the concurrency. So it can be used to cancel no longer needed MySQL queries. So say maybe the client canceled the HTTP request. The initiated query wouldn't be any more use. So we can just cancel it and save MySQL CPU. And timeouts are the same. So yeah, I think embracing concurrency as an ecosystem is needed to make Ruby have better chance to win ISUCON. So wrapping up, it's really fun to write Ruby. Profiling is important, but it's more important to check if those profiles are accurate and check other things. So let's do ISUCON. So I'm going to want to deliver acknowledgements. Saichi-san and Koba 789-san. 789 is 789. It was just Japanese. They are my longtime ISUCON teammates. We've been doing this for a long time. And I also like to thank Koichi-san and Mame-san. They're my co-workers, and they give us many valuable advice. So thank you. And that's the end. Thank you.